Good morning friends. In this video we are going to see the input and output characteristics of NPN transistor used in common emitter configuration. Here we can see the NPN transistor, the symbol of NPN transistor and PNP transistor. The main thing you can notice here is, the first thing is the direction of the emitter current. In NPN transistor, you can see the arrow mark is pointed outwards. The direction of emitter current is out from the transistor. In a PNP transistor, direction of emitter current is inside towards the transistor. The next is the direction of the base and collector current will be opposite to the direction of the emitter current. If you see here, the direction of emitter current is outside from the transistor, so the direction of base and collector current is into the transistor. Similarly, for a PNP transistor, if you see, the direction of the emitter current is into the transistor, the direction of the base and collector is out from the transistor. So here I have shown the symbols for NPN and PNP transistor. If you see here, in here I have connected, I have shown the figure for NPN in CE configurations. CE stands for common emitter. This is the input. Here in CE, input is base, output is collector. So emitter is common to the input and the output, and here emitter is grounded. You can see the direction of base and collector is into the transistor and the emitter current is out from the transistor. Now we will see the input characteristics of NPN transistor. Here we can see the NPN, emitter base collector. Now to get the input characteristics, we have to note down what is the value of base current for different values of VBE. So VBE is the voltage between the base and the emitter, which is shown here, VBE. So what we have to do? We have to increase VBB. So the increase in VBB will lead to increase in VBE. So for different values of VBE, you have to note what is the value of IB. We can see that around some 0.7, when VB is around 0.7, we can see a sharp exponential increase in current. Okay, usually we will call it as cutoff voltage, where VBE on equal to 0.7 volt. Okay, which means that when VBE is around 0.7 volt, this is volt, and this will be around some microamps. When VB is around 0.1 volt, this emitter base junction, is forward biased. So this is the input characteristics of NPN transistor in CE configurations. Now let's move to the output characteristics. In output characteristics, we have to plot IC, which is the collector current, versus VCE, the voltage between the collector and the emitter. Now let's see here. So the emitter base junction is forward biased. The VBE is across this junction. So let me call it as, this is plus and this is minus, this is VBE. Similarly, this junction is called collector base junction. We will note it as minus plus BCB. If you write as BC, you have to change the sign accordingly. So this is the emitter base junction and this is the collector base junction. Now we can see here, we have to increase BC. For different values of VCE, we have to plot IC. Now what happens here is, so the voltage between the collector and the emitter. So if we take this is VCE. Okay, now if you write a loop around here, we can write it as VBE minus VCE plus VCB equal to 0. So VCB equal to VCE minus VBE. Okay, so now what happens here is, when VBE is, assume that VBE is around 0.7 volt, which means this is forward biased. The emitter base junction is already forward biased. Now what happens when VCE is less than or greater than VBE? We can classify this into two cases. First we will say when VCE is greater than VBE. VBE represents, VBE is now 0.2, 0.7 volt. So when VCE is greater than VBE, which means VCB is positive. When VCB is positive, here see when this collector base junction is positive, which means the junction is reverse biased. Thus, when VCE is less than VBE, which means when VCE is less than 0.7 volt, so VCB is negative, which means the collector base junction is forward biased. Now what happens when the collector base junction is reverse biased, when the collector base junction is forward biased? We have already seen in the last class, the electrons which reaches the collector base junction will swept across the junction to reach the collector. That will happen when the collector base junction is reverse biased. So we will get a constant collector current biased. When the collector base junction is forward biased. Now both the junctions are forward biased. What happens? The electrons from the emitter enter into the base. Similarly, the electrons from the collector also enter into the base. So the direction of electrons are opposite, so the current will cancel, which make collector current eventually goes to 0. So we can see here this part when VCE is less than, this 0.7 volt, which is this case, the collector current is eventually going to 0. Okay, so which means that this region where the VCE is less than, where the VC is less than VB, this region is called as saturation region. And this region where VC is greater than VBE, you can call it as forward active region. So now here the collector, we have said that the collector current is constant, but you can see there is an increase in collector current as VC is increased. This is due to base width modulation. We will see what is called base width modulation. Discuss about early effect or base width modulation. We can see this. This is the emitter base junction and this is the collector base junction. Now I will draw this collector base junction alone. This is P side and this is N side. This is the depletion width. This is the depletion width. And here this is the N side. What happens here is electrons is injected from the emitter to the base, and here is the electron will reach us like the whatever the electrons will approaches the collector base junction will swept across the junction due to the strong electric field in the depletion width. Now what happens here when the reverse bias in the increase? If we increase the reverse bias in the collector base junction, what happens? The depletion width is increased. Usually the collector is very lightly doped when compared to the base, so that the depletion region will extend into the collector. But a small amount of depletion width will extend into the base also. Now this is the new depletion width when there is increase in the reverse bias. Okay, due to the extension of depletion width into the base, now the slope will go like this. Now you can see there is an increase in slope. So when the depletion width is increased, the slope of the minority carriers is now increased. The slope of the minority carriers is proportional to the current. So because of this, there is an increase in the current. So here we can see there is an increase in the collector current as VCE is increased. This is called base width modulation. We can see the output conductance 1 by R naught is equal to the change in the current, change in the output current IC with respect to change in VC. You have to extrapolate these curves to get this VA. This VA is called early voltage.